As aerospace engineers, it is important to understand how useful a wind tunnel is to analyze the aerodynamic performance of an object. A cylinder, although a simple shape, generates a complex flow field in the wind tunnel. Throughout this lab, important concepts such as flow separation, pressure drag, and aero analysis were utilized to understand the airflow over a cylinder in a wind tunnel. The main goal of this lab was to analyze the effect of surface roughness and Reynolds number on flow separation and visualization of vortex shedding related to the quantitative and qualitative characteristics of fluid flow. The pressure drag trends that were calculated based on the pressure readings were compared to a theoretical solution. The team hypothesized that the coefficient of pressure would decrease with addition of the trip strip due to a delay in flow separation.
Throughout the experiment, the following nomenclature will be used. Some key nomenclature to focus on is theta, where it is the angle around the cylinder from the stagnation point or the leading edge. Pi is the pressure at each pressure port, which is used to calculate the force of drag and are in units of pascals.
In this experiment, the team analyzed two major concepts, flow separation and pressure drag on the cylinder for different surface roughnesses. In a slow laminar fluid flow, friction and pressure drag are equally prevalent, but at moderate to high Reynolds numbers, pressure drag is a dominating drag force. As air flows over a cylinder, flow starts to detach from the surface. When air flows far enough against the pressure gradient, the relative speed between the surface and the boundary layer is zero. With flow separation, pressure drag increases due to the pressure differences between the front and back of the cylinder. Once the flow separates, vortex shedding occurs at a certain frequency, which can eventually lead to structural failures such as a result of aeroelastic flutter. As shown in Figure 1, vortices are generated from the upper and lower hemispheres of the cylinder after the flow separates from the surface.
The following are the key assumptions.
In this experiment, the team used a low-speed wind tunnel, P80 sandpaper, laser, fog machine, cylinder, tape, MATLAB, and LabVIEW to achieve the experimental goal. A 1.2 meter long and 0.114 meter diameter cylinder was used to analyze the flow over a bluff body. The cylinder was placed 1.77 meters from the beginning of the test section and 0.44 meters above the test section floor, as shown in Figure 2. To analyze the effect surface roughness has on the airflow, P80 sandpaper was used to trip the airflow over the cylinder.
Pressure ports were placed around the circumference of the cylinder every 15 degrees for a total of 24 pressure ports as shown in Figure 3. There was an additional port at the beginning of the test section to measure total pressure. Pressure port 12 was located at the leading edge of the cylinder, also known as the stagnation point, and pressure port 24 was located at the trailing edge. At the inlet, a fog machine was used to visualize the airflow over the cylinder. A laser was placed above the trailing edge of the cylinder to clearly visualize flow separation and vortices created. Aluminum tape was used to safely secure the sandpaper from flying away in the wind tunnel. To achieve the goal of this experiment, the team operated the wind tunnel at two velocities, 3.5 meters per second and 20.5 meters per second. Velocity was determined to allow flow separation to occur at different locations on the surface of the cylinder. To increase accuracy, 3 sets of data were collected for the cylinder with and without the trip strip at different velocities. The trip strip was placed symmetrically on the upper and lower hemispheres 70 degrees apart from the leading edge. This was because the airflow was separate about 70 to 80 degrees as shown in Figures 4 and 5. Throughout the experiment, team members analyzed the flow visualization of the cylinder with the assistance of the fog machine and laser. After each trial, a member validated the pressure data to ensure no discrepancies occurred.
There were multiple sources of error for this lab. A major source of error was the location of the trip strips. For low velocities, the location of the trip strips were not able to create turbulent flow around the cylinder. This error is discussed later on. At higher velocities, trip strips were able to trip the boundary layer into a more turbulent flow. Another major source of error was the fluctuations in wind velocity caused by inconsistent RPM of the fan. The wind tunnel did not produce constant air velocity, which caused the Reynolds number for each experiment to fluctuate. This caused a slight discrepancy in the steady flow assumption used in the Bernoulli equation for calculating velocities for pressure data. The orientation of the cylinder in the test section was not perfectly aligned with the free stream. The pressure port at the 0 degree angle was not aligned with the stagnation point, which yielded a non-zero velocity where the stagnation point would have been. After obtaining experimental data, the team analyzed and extracted important information such as coefficient of pressure and coefficient of drag in order to validate the hypothesis of the coefficient of pressure decreasing with the addition of the trip strip due to a delay in flow separation.
In this video, you can observe a Von-Karman vortex sheet, which is a repeating pattern of swirling vortices caused by the unsteady separation of flow of a fluid around blunt bodies. With the trip strip, the flow stayed attached to it for a longer time. On placing the laser perpendicular to the flow, we were able to observe eddies in the flow. At a higher Reynolds number, we can see a larger wake behind the cylinder, resulting in a low pressure region behind the cylinder.
To obtain the coefficient of pressure plot, coefficient of pressure was calculated using equation 1. Figure 6 shows that there is a positive coefficient of pressure at the beginning of the cylinder and in the wake region, and a negative coefficient of pressure at the upper and lower surfaces. Results for the upper surface of the cylinder show that the coefficient of pressure of the cylinder decreased with the addition of a trip strip. Figure 7 and 8 show the relation of the coefficient of pressure to its location on the cylinder. The circles on the graph represent the point of separation. At 0 degrees, coefficient of pressure is the highest because maximum pressure occurs at the stagnation point where the velocity should be 0. When analyzing the graph, the coefficient of pressure from the experiment compared to theoretical values were very similar up until 60 to 70 degrees. In Visit, theoretical values increased after 90 degrees, but experimental data converged to a value of coefficient of pressure. The reason for this is because the theoretical plot assumes a laminar flow that stays attached to the cylinder at all times. In the experiment, the flow separated around 75 degrees for all experimental trials except for the case of 20.5 meters per second with a trip strip applied. The trip strip caused the boundary layer to be turbulent, which kept the flow attached to the cylinder surface longer than the trials without the trip strip. The effect of the trip strip on the flow separation at low speed is not entirely noticeable, but begins to be noticeable at a higher speed. At 20.5 meters per second with the trip strip, the flow separated at about 105 degrees, while the flow separated at 75 degrees with no trip strip, as shown in Figure 8. Due to flow separation, it resulted in a large pressure difference from the leading to trailing edge of the cylinder. Pressure was a lot lower at the trailing edge than the leading edge due to the presence of a wake region. Figure 9 provides a visual representation of flow separation. The beginning of the color gradient denotes the beginning of flow separation. When the trip strips were added, the flow stayed attached to the cylinder for a longer distance about the cylinder as shown in the bottom plots. For the lower surface of the cylinder, flow with the trip strip separates later than on the upper surface plot because of the previously stated asymmetrical orientation of the cylinder to the free stream. Theoretically, the coefficient of pressure should be the same at the upper and lower surface since the pressure ports were spaced out symmetrically.
The panel code method was used to calculate drag because a force balance was not used during the experiment. Figure 12 shows the approach to the panel method. Please note that the figure does not fully illustrate the number of panels used. In this method, each port is modeled as a panel on the cylinder. The force of drag was calculated using the x direction of the pressure on each panel and then multiplied by the area of the panel. The sum of all the panels is the force of the drag on the cylinder as outlined in equation 2. Table 1 shows the force of drag for each wind tunnel speed. Theoretically, the force of drag should be lower when the trip strip was introduced. However, that was not the case at 3.5 meters per second due to inaccurate placement of the trip strips at 70 degrees, so it was not useful in tripping the boundary layer since the flow was laminar. At velocity of 20.5 meters per second, the coefficient of drag follows the theoretical trend more closely because at higher Reynolds number it is more useful to trip the boundary layer sooner in order to maintain attached flow to the cylinder surface. Using the drag force calculated in Table 1, coefficient of drag can be calculated using equation 3. As showed in Table 2, the trip strip caused the coefficient of drag to increase at 3.5 meters per second and decrease at 20.5 meters per second compared to no trip strip.
Using the experimental pressure data, Reynolds number was extracted at each pressure port. Before calculating Reynolds number, velocity had to be calculated at each pressure port using Bernoulli's equation as outlined in equation 5a. To calculate Reynolds number, equation 4 was used. Figure 13 portrays the Reynolds number about the circumference of the cylinder at different surface roughnesses and wind tunnel speeds. At wind tunnel speed of 3.5 meters per second, small Reynolds numbers were produced for trip strip and no trip strip. The trip strip induced a slightly higher Reynolds number towards the trailing edge of the cylinder, but it did not produce a turbulent flow regime. This was because the trip strip was already located in the flow separation area, so it could not trip the flow and cause turbulence earlier on in the cylinder's boundary layer. However, when the wind tunnel operated at 20.5 meters per second, Reynolds number was obviously higher than it was at 3.5 meters per second, so turbulent flow was considered about the surface. The trip strip produced higher Reynolds numbers towards the trailing edge because it was able to trip the boundary layer earlier on. Tripping the boundary layer energized the flow, causing increased stream velocity in the boundary layer, which was why the Reynolds number increased with the trip strip. When Reynolds number is greater than 200, wake vortices are considered three-dimensional, so this entire experiment produced 3D wake vortices, while only 2D flow was examined in this experiment. The free stream velocity was not affected by the introduction of the trip strip, nor was it affected by changes in tunnel speed. This shows that the conditions observed remained consistent from trial to trial.
In conclusion, applying a trip strip to a test cylinder at 70 degrees on both leading sides of the cylinder yielded a lower coefficient of drag similar to the theoretical calculations. This effect is more noticeable at higher Reynolds number, which reduces the amount of pressure-induced drag in the wake region of the cylinder by creating turbulent flow. At 3.5 meters per second, flow separated at 75 to 80 degrees in both cases. At 20.5 meters per second, the trip strip caused the flow to separate at 105 to 110 degrees, nearly a 30-degree difference. Surface roughness plays a major part in the aerodynamics of an object in a flow field. Typically, a little bit of roughness placed accordingly to the object's geometry will allow the flow to stay attached to the surface of the object longer, decreasing pressure drag. However, too much surface roughness causes the coefficient of friction to increase, which increases the overall drag of the object. It is ideal to have a slight increase in the surface roughness right before the flow separates from the surface, and have the rest of the object smooth in order to minimize frictional drag. One of the most common applications of delaying flow separation is of a golf ball, where the dimples are used to create a recirculating region that allow for the free stream velocity to flow closer to the surface of the ball. Some real-life applications where cylinders are present are struts in aircraft, flagpoles, and large building structures. The aerodynamic properties of these cylinders must be taken into consideration when designing these products in order to maximize these structures' drag characteristics. Due to its importance in real-world applications, this lab plays a vital role in understanding basic fluid flow characteristics of a cylinder.